We're going to talk about magic squares of squares. So first thing we're going to do is talk about what a magic square is. We're going to start with a 3 by 3 grid. We're going to have 8, a 1, and a 6, and a 3, and a 5, and a 7, and a 4, and a 9, and a 2. So this is a 3 by 3 array of numbers.
Classic.
And what's incredible here is that if you add the numbers down the columns, so like 8 plus 3 plus 4, you're going to get 15. You're going to get 15 no matter what column you add down. Or if you look at the rows and if you add those up, then you also get 15. So all the rows add up to 15. And also the two diagonals. So the principal diagonal.
Show off.
This is 5 plus 2 is 7, plus 8 is 15. And then if you look at the other diagonal, so 4 plus 6 is 10, plus 5 is 15. So everything adds up to 15. So columns, rows, and the two diagonals add up to 15. That's a perfect pure magic square. In fact, this is the earliest, or up to some sort of rearrangement of the numbers. It's the earliest known recorded magic square. It's usually called the Lo Shu. There's records of it from about 2200 BC. The Chinese tradition has it that the emperor
That's old school.
saw this magic square on the back of a turtle. It's a sort of beautiful story.
I know there are lots of other magic squares. We're going to talk about them shortly.
Yeah.
Is a magic square still a magic square if any number is repeated, or is that kind of imperfect?
So I would argue that those are imperfect magic squares. And in fact, that's kind of
Controversial
what makes it hard
statement.
to find magic squares. If you allow repetitions, you can really find magic squares quite easily, right? I could just repeat all the numbers here, right?
Quite easily.
Your favorite number, mine is 19. I think it would be 9, but 9 is not prime, so it's 19. So if I put 19 everywhere in these 9 entries, I'll just get a magic square that way. But it feels like it's not a real magic square. It feels like a fake magic square. So what I want to do is look at 3 by 3 magic squares, but I want to impose one more condition, which is that I want the entries themselves to be the squares of numbers. So I'm going to draw for you an example of this, and it'll be a bit of a cheat. People
What a new concept.
Numberphile videos for a while are going to recognize this. So this is 29 squared, 1 squared, 47 squared, 41 squared, 37.
Oh, this
squared,
video has just
1
picked up
squared,
immensely.
23 squared, 41 squared, and 29. And this is a very
Art.
famous
Very
magic
famous.
square, and it was made famous by Numberphile. So this is the Parker square.
So I'm not calling
Yeah,
it the
just by
Parker
Numberphile.
square.
You know what this video is
I'm
called?
calling it up for crying out loud.
This was famously Matt's attempt at all squares.
That's right.
back
that's
when
right.
I had
It's a
hair.
very good attempt. I think this is a very reasonable attempt. In fact, it complies
Very
with almost all
reasonable.
the requirements of
Almost,
a magic
almost.
square of squares, right? So every single entry is a square number, right? And it's true that if you add up all the rows and all the columns, and if you add up the two diagonals, it all adds up to the same number. So it satisfies the main requirements for being a magic square.
Doesn't one of the diagonals fail?
Wait, sorry, can we check that?
This diagonal here works. This diagonal
enough, that's
here
enough.
doesn't
That's-
work.
One of the diagonals does not. And so in that sense, it's not quite a magic square of squares. It's what people tend to call a semi-magic square. And there's some repetitions of the entries. So for example, you see the 2 1s here, you see a couple of 29s, a couple of 41s. And so it sort of feels like it's cheating
perfectly
just a
good.
little bit. But it's a really good attempt. Okay, so it's a good starting point. Sometimes in math, when you can't solve a really difficult problem, you try to solve a simpler problem. And making some of these
That's very
allowing some
true.
of these
Very,
numbers
very
to
true.
be, the same as a way of
I
trying to
allowed them.
simplify the problem that and in a way that might use some interesting mathematics as well.
Okay, Parker square.
Great.
Good attempt.
Yes. Okay. So there are a couple of other squares that I want to show you because so as we saw in the Parker square, there's just a couple of things that aren't quite right. And there are some really famous ones. These are sort of from the late 90s. So one of them is called the Bremner square. Okay, this is a big one. Okay, so this is another attempt at a magic square of squares, and it's very good in sort of a different way from the Parker.
It's fine.
This
It's
time
fine.
you'll notice almost immediately
Very
there's
90s.
two entries that are not squares. That's where this fails.
That
But-
feels like an even more fundamental.
It was the
problem,
90s.
right?
Yes.
Are they close
Yes.
to being squares?
Not really. I don't think it is a little bit sad that they're not really squares. But what is true here though is that the columns and the rows and both diagonals add up to the same thing. So somehow we managed to at least preserve that property, but then we broke the squares. We do have distinct entries. So you know, you feel like you're making progress. I mean, it'd be, you know, cool to have one that had like 8 squares, you know, and maybe only one that's not a square. I don't know of one, and I'm not sure if one has been found yet. There's another square consisting of square entries, which is almost a magic square. It's a semi-magic square. It's by Sallows, and in a sense, it's sort of an improvement on the Parker square in that all the entries are distinct. However, just like with the Parker square, one of the diagonals doesn't add up to the same number that all the others add up to.
That feels like one of the best attempts so far, doesn't it? Like,
That's right. Yes. In fact, it's really nice that if you just remove one of the conditions, then you really can find them. It's a very difficult problem precisely because of how all of the conditions come together.
of course,
Very
this is a
difficult problem.
fundamental question here. Does one exist? Has anyone ever found a magic square of squares?
As far as I know, no. It's really sad. And in fact, what I want to do today is try to convince you that there probably isn't one. Okay. So I know that's sort of a sad thing to say. I would love it for it to be a magic square of squares. But I think sort of geometry is giving us a bunch of indications that this just might not be the case.
They
So,
better
in fact,
back that up.
What geometry suggests is that if there is a magic square of squares, it's going to be really, really difficult to find.
This is going to be good. You know what? I need some
Beyond what
popcorn for this.
we can do
Can I
by
get some
just
popcorn, anyone?
small things.
This doesn't look like.
Oh,
geometry to
thanks.
me.
Right.
Here we go.
Oh my God, yes. Thank you
All
for
right.
that question. Yeah. Let me try to show you where the geometry at least starts coming up. Let's do it. So we're trying to find 9 numbers, each of them a square. And so I need to give them names. I'll call them x1 squared, and x2 squared, and x3 squared, and so on. What we're hoping for is 9 distinct positive integers, x1 through x9, that I can put into one of these 3x3 grids in such a way that the rows, the columns, and the 2 diagonals add up to the same number. And so I can actually write out what those conditions are in terms of just algebra. Right? I can
Like a big monster equation. or-
yeah, it's going to be a set of monster equations, in fact. So let me show you. So for example, I need to know that the first row is equal to the sum of the elements of the first row is equal to the sum of the elements in the second row. So I can just write out this monster equation. Okay. I also need the same two
Already a
sums
monster.
to equal the sum of the third row. So I can write another equal sign here. This all has to be the same. Okay. I also need to know that this sum is the same as the sum of the 2 diagonals. So let me do those next.
Yep.
So there's x1 squared plus x5 squared plus x9 squared. And then the other diagonal, so it'll be x3 squared plus x5 squared plus x7 squared. This is a bit messy, but we still have to do the columns. So the first column will be x1 squared plus x4 squared plus x7 squared. Okay, and then I'll do the second column. X2 squared plus x5 squared plus x8 squared. Okay, and I'm still missing.
Genuine fun fact.
Okay, but here's
A lot of
this is
people have sent me
really important
emails
observation. So once I know
that start
all 3 rows add up
with
to the
that
same
setup
number,
in geometry.
and the first 2 columns add
So many emails that are just like,
forces
oh,
the
you can
last
do some
column to add
equations.
up to the same number as all the previous rows and columns. And so this last thing is not a condition that
I
we
think
need
this
to
person's going
set out
somewhere
because
with it
it's
though.
already implied by all the other ones that we have imposed. So this is sort of an important thing because it cuts down on the number of equal signs that I've written. Okay, so there's only 1, 2, 3, 4, 5, 6 equal signs. I don't need one more equal sign to say that this is all equal to the sum of the last column. That's an important geometric point. Okay, so we have a mess here. So we have this like huge system.
It's because those ones are kind of left over.
So I need to make sort of
If
a
you've already got the
observation about
constraints
this
for the other
equation.
2 columns.
What I want to try to argue soon is that it's going to be really difficult to try to solve this particular system of equations with the extra requirements that all these x's are different. Okay, and this is really sort of the important bit.
I feel like you don't have to make that argument to me. It already looks difficult, but all right. Do you want more paper?
Sounds good. Yes. We have 9 variables, and we have these 6 equations. And so I want to think of these 9 variables as like a point in some kind of space. And this space.
This is great. Everyone now who emails me,
Okay.
like, have you considered doing the algebra? I can just reply with this video.
In some kind of 9-dimensional space, you know, like usually we have like a 3-dimensional space that has like x, y, and z coordinates. There's only 3 coordinates. Here I'm going to need a space where I can write
Z.
down 9 coordinates. Okay, so that looks like it could be a 9-dimensional space, but there's something really special about the equations that we have that allow me to cut things down sort of by 1 dimension. Instead of sort of, even though I'm going to write my points using 9 coordinates, there are really sort of only 8 dimensions that are in the works. In the same way that we talked about, some squares feel like, they might be a little fake, there is a sense in which some squares, even though they appear different, they feel like in our bones they're kind of the same. Okay, and let me kind of show you that with something that's probably a little more familiar, which is sort of the Pythagorean
A lot of
triangles.
maths is
This is a
feeling
very
things in your
famous
bones.
Triangle, the 3, 4, 5 triangle, and we have that 3 squared plus 4 squared is equal to 5 squared. Right? This is that Pythagorean relation. But it's a different triangle, but this is going to be a 6, 8, 10 triangle. And there's something funny about this, which is that, okay, it's
Same
still
thing.
true. So 6 squared plus 8 squared is equal to 10 squared. But somehow these
The
triangles
same
don't really feel
triangle
that different.
wearing a
I just
disguise.
took this triangle and I just kind of scaled it up. In a sense, the triangles literally are different, but they don't feel like a genuinely different triangle. It looks like I just took the triangle I already knew and I scaled it up. And the same thing is going to happen with things like magic squares. It doesn't even have to be magic squares of squares, right? There's the low shoe, and so I can just take the low shoe and just multiply everything by 2. So I'm going to put a 16 here, and a 2 there, and a 12 there, and a 6, and a 10.
It's one of the steps you do
14, and
if
an
you're doing the
8,
trick where you
and
generate a
then,
magic square for any
18,
possible
and
value.
4. Okay, and
I
now
think that was
everything
in my
adds up to
original
30 this time. But that's not very
extended
surprising, right?
Numberphile
I
video.
just scaled every single number by 2.
from back in
So
the hair
the
era.
equations that give you a magic square, it's just like multiplying those equations by 2. And so this doesn't really feel like a genuinely different magic square from the low shoe. In a literal sense, it is different, but somehow it sort of came from the same mold. And so that's really the important thing, is that when we look at all of these coordinates and I multiply them by 7, when I look at my magic square of squares, each one of these entries will get multiplied by 49, because 7 squared is 49. And so every single entry will get multiplied by 49, and then it'll still be true that the rows and the columns and the 2 diagonals will add up to the same. Any solution to this problem, and I scale it up or down, I could also just have fractions instead in there, I'll still have a magic square of squares. So these solutions have this very nice scaling property. And what that means is that even though you see sort of 9 coordinates, you only really have about 8 degrees of freedom. So the reason that's important is that the natural habitat for these equations is something like an 8-dimensional space. What do I mean by the habitat of an
good
equation?
space.
So let me just remind you, if I just worked in the usual plane where I had x and y coordinates, so I had 2 coordinates, I have 2 dimensions, I can look at an equation like this, x squared plus y squared equals 1. This is one equation in this 2-dimensional space, and it cuts out for us a circle of radius 1. X squared plus y squared equals 1. And so what we're doing here is something similar. It's just much harder to visualize because I'm going to work in a space that technically has 9 coordinates, but only really 8 degrees of freedom. And inside that space, I'm going to look at the solutions of some
The trick
big
is to
set of
imagine it
polynomials, and this set of
in,
polynomials will carve out a
like,
geometric shape,
18
just like
coordinates,
x squared plus y
and
squared
then
equals 1 carves
simplify
out
it down.
a geometric shape on the plane. It's just that it's hard to visualize 8-dimensional space. So I don't know how to draw that here, but the object is out there and it exists.
So not only is that impossible to imagine the playing field, you also don't even know what the configuration of the players are.
Right, that's right. Yes. So we really
Brady
have to sort of use
trying
our
to sneak some
imagination and the
sport
algebra. This is sort of a
into
really
the video.
important idea that we're
He does that.
trying to do some
Watch.
geometry, but when we can't visualize things, sometimes the algebra is still there and we can work with the algebra instead of the geometry. So we have this 8-dimensional space.
I think it's worth
and if you
reflecting,
look back at
ignoring
the set
Brady's
of
sport thing.
equations that we wrote,
It's a
there were
real
6
shape. That
equal
shape
signs.
exists.
And so
Doesn't matter that
each
we
one of
can't
these equal signs
perceive it or imagine it. It's out
constraint
there.
on this 8-dimensional space. So you start with
And
this
only the
8-dimensional
brave
space, and then
try
I
and
put a
hunt it down.
constraint in it. And so now what I'm holding is probably a 7-dimensional.
It doesn't look like that.
And then I put another constraint in it. And so now these 2 constraints have to be satisfied simultaneously. And so the intersection is probably something that's 6-dimensional. And I keep doing this. And if I have 6
It's a good
constraints,
representation of the
well,
concept.
okay, I'm just going to write 8 minus 6 is equal to 2. Once I sort of put all these constraints together, it looks like what I should have is some kind of surface, some kind of 2-dimensional thing. Each constraint is sort of cutting me down in 1 dimension. I started with 8 degrees of freedom, and I've taken away 6. And so even though it's very hard to actually visualize something like this, it looks like it could be some kind of surface.
So there's some 2-dimensional surface that would hold the key to everything.
Exactly. This is exactly the point. There is this sort of incredible, now I'll just do like a metaphor for it. There's this 2-dimensional surface, and each point on that surface is going to have coordinates x1, x2, all the way to x9. And this point encodes one of these magic squares of squares. Now what's important...
Has this surface got a name?
No.
Can I suggest one?
What would you like to call it, Brady?
The Parker surface.
That's awesome. All right. Okay, let's call it the Parker
Awesome.
surface. Yeah, so any point on the Parker surface is going to give you a magic square of squares. Now,
It's never
the
gonna
surface
die.
really is there. I think one of the
This poor
things we have to
person's worked
realize
very
is
hard on
that
this.
these X's could also be
And Brady's
not just
bullying him into
we are looking for
naming
integers,
it the
we want
Parker surface.
But you know, if I just sort of write out these equations and I let x1 through x9, you know,
Kinda cool, I got my own
more
surface though.
general numbers, I mean like pi or e or you know something with an infinite decimal expansion that's random, those are perfectly good numbers too. And so what happens is that this square is there, but almost every time you write one of these points down on it, there's at least one coordinate that's just not going to be an integer or a fraction. And so what we're really trying to do is, you know, our job is to try to find points on the surface, all of whose coordinates are integers and distinct.
Yeah, a rational point.
And this is where things get tricky, because inside this space, right, you can actually take something that looks kind of like a plane, and then it'll sort of cut the surface, and this will be, for example, the locus where like maybe two of the coordinates are the same. That could definitely happen. And you know, things like the Parker square, you know, have the property that some of the entries are the same. And so, for example,
It's a
it can
property.
be a point that happens to lie there. And this is the tragedy that we seem to face, is that on this surface, every time we have a point that seems to give us a magic square of squares, these points tend to lie on these very special curves.
It's a
of the
tragedy.
surface, where you have conditions like, you know,
It's like that
x1
song.
is equal to x2, or x3 is equal to minus x7, or you know, something like this.
Because when you first told me about this surface, I thought maybe there'd be no points on the surface where all of them are integers, but there are some there, so...
That's exactly right. And this, you hit on something really important, Brady, which is that this is what makes this
By
problem
accident.
really difficult, is that this surface really has points with integer coordinates. It's just that we don't like the points that we see. There's also the one where you set
Yeah.
everything equal, just put everything...
Get a lot of feedback about people not liking the points.
3 is equal to 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 3. That'll work.
This surface is obviously of infinite size.
Oh yeah.
Yeah.
Yeah, there's lots and lots of points on the surface.
Yeah.
So when this is what makes it hard. So in there's this area of math called Diophantine.
That's why it's called the Parker
that
surface.
tries to exactly solve.
I have a
this
lot of good
problem,
points.
Where you take a collection of polynomial equations, like the ones that define the magic square of squares, and they try to find integer solutions, or prove that there are no integer solutions, other than sort of, you know, a few obvious ones that we see, but that we're not really interested in. The same thing happens with Fermat's last theorem, which is really aggravating. You know, Fermat's last theorem has solutions, right? You know, 0 to the n plus 1 to the n.
That's why it's
equals 1 to
considered
n.
the easier problem.
So the Fermat equation.
Okay, that's enough.
What makes it
That's
really
enough popcorn for now.
to show that there are no solutions other than, you know, the solutions that contain at least one zero. Okay, and that's a much more difficult problem. In math, we have all these, you know, this whole slew of techniques for showing that systems of equations have no integer solutions whatsoever. But that's not the case here. There are integer solutions. So what we're trying to do is to show that there aren't solutions other than the
Fermat.
ones that we actually see.
Parker.
And that's a much more difficult problem to solve.
You told me earlier that you've come to the conclusion that it's really unlikely that one of these exists. What you have shown me so far has made me more hopeful that one exists.
Yes,
Yeah.
I understand what you're. So why do I think that one might not exist? Okay, yeah, I guess I did. Yeah, I need
More
a new
paper.
sheet of paper.
More
yeah,
paper.
to-
Take away my hope.
Okay, so I'm going to try to explain why I think that even though we have this huge surface worth of points, all of which actually give you a magic square of squares, there's just no point where all of the entries are integers and they're distinct. Why do these points even exist in the first place? And so this is a philosophical point, but it's, you know, points that satisfy polynomial equations that are, you know, all integers are very, very rare. They're sort of almost accidents of nature. And this is sort of something really important to bear.
I'm just going to react
So we
briefly.
know
It
if
says
instead of
continues to be considered a derivative work.
curves come in sort of three flavors from this sort of integer arithmetic point of view. The first one is called rational, and in fact, the circle that we were looking at before, this is kind of a perfect
Everything I do
example
is
of
considered a
rational
derivative
curve.
work,
What makes
but hey.
these curves themselves have lots and lots of points that have either rational or integer coordinates. You know, here's already a point on the surface, 0, 1. If I sort of take the line that connects that point to some number t on the real number line, then I can do a little bit of analytic geometry and compute this thing. You'll see that it's 2t squared divided by t squared plus 1, and then t squared minus 1 over t squared plus 1. This actually has to do with Pythagorean triples, but that's a story for a different day. What's important here, you see, is that if t is like an integer or some rational number, then these expressions are also going to be integers or fractions more generally. There's heaps of rational numbers on the real line. And so I just pick some rational number t, and I do this construction, and it gives me a point on my curve that has a rational coordinate. So rational curves have this
It's the rational thing to
property
do.
that the moment you have one point, okay, I need 1 point to get started, then I can use that 1 point to construct lots and lots and lots of other points. Then there's elliptic curves. So elliptic curves sort of have this funny kind of shape, usually. They're defined by cubic polynomials. Elliptic curves have this incredible thing that you can add points on them. Okay, so if I take p and q, okay, this is not p plus q, but if I just sort of reflect it down, I can call this p plus q. And this sort of crazy little construction that I just did happens to actually sort of satisfy things like associativity.
That's a
which is
whole
something
thing.
that, you know, if I have three things, you know, I can move the parentheses around. So elliptic curves have this crazy property that you can add points on them. And the reason that's important is because it allows you to also create new points out of old points. So if I have an old point, I can add it to itself, for example, and then create a new point. And then I can add that point to itself and create a new point. And so elliptic curves have also this property that if I start with a point, I can propagate it. So rational curves are great. Elliptic curves are great in that, you know, they can come with lots of points. And then there's general type curves, and those are sort of, well, they're sort of more complicated, but
They're the
one
higher
thing that's
ranking
amazing is that
curves.
they always have finitely many points with coordinates that are rational. This is a spectacular theorem from the early 80s, maybe 1982. It was proved by Faltings, and he got the Field Medal for this theorem. So this
A lot
is
of great things come from the early
It
80s.
was called the Mordell conjecture back then, and now it's Faltings theorem. What we have is not a curve. Okay, it is a surface, but I'm telling you this story because it actually plays a very key role in our surface. So when we have curves, they sort of come in three different flavors. Two of those flavors have lots and lots of points, and one flavor does not. So what happens with the surface that we were calling the Parker surface, right, is that as a consequence
That's
of
'cause
some
it's
work
its
that me
name.
and a couple of co-authors, Nels Brown and Jordan Thomas, were working on, is we managed to show that on this surface right here, there are only finitely many curves of these two types. And this is really something that surprised us.
So a surface is full of curves, made of curves.
Exactly. You can take a surface and just like chop it up into lots of curves. And then, you know, if you're looking for points on that give you a magic square of squares, one thing you might try to do is, instead of looking at the whole surface, just look at a curve inside that surface. And maybe you get lucky, and maybe your curve is one of these two types, and then you can use what we know about these two types to actually construct magic
See,
squares of
this
squares.
is
But
the
sad
mathematics
thing
you got to
is
do.
that
For everyone who just
the
emails me with the
surface,
equations
the
and a bunch of
parameterized magic squares
GeoGebra,
squares, the Parker surface,
sorry, algebra,
has
and geometry.
only finitely many
Uh,
of these rational.
No, you need to actually
It doesn't only need one.
investigate it
It
and
only
discover
needs one.
things.
You're right, but here's the crazy thing is, it has more than one. In fact, this Parker surface has 368 of these curves that we know of. So there's at least 368 of these rational or elliptic curves. The sad thing, though, is that the way we've constructed these is that we looked at slices like this. You know, what happens if I take x1 equal to x2, that gives me some kind of curve on the surface. And then either this curve or, you know, the curve itself might break into a few pieces when I do the slicing. You know, those individual curves are either rational or elliptic, but they have this property that x1 is equal to x2. So the 368 curves that we can find, they contain points, but all of the points on these curves are going to give us these kind of fake magic squares, which is really, really sad. Okay, and so here's the final kicker, though. There is a conjecture. So Parker surface.
Conjecture.
So this has finitely many rational and elliptic curves. So our idea to try to use these curves to produce points it isn't looking so good. Like I say, this is some theorem that came out of work that me and a couple of co-authors were working on, and I mean it was kind of neat. I mean, we didn't expect that we would be able to prove something about this very specific surface. But now the kicker is that there's something called the Lang-Voida conjecture. This is the incredible thing. This surface that we have here is a particular kind of surface. It's also called the general type surface. And Lang and Voida sort of made a series of very deep conjectures. But when you apply those conjectures to the surface, what it says is that outside of the rational and the elliptic curves, there can be at most finitely many points on this surface.
It's finite all the way down.
Right? There's tons and tons of points on the surface, but there's only going to be finitely many points outside of this nice locus of rational elliptic curves, all of whose coordinates are going to be integers. There's finitely many, I'll call them rational points outside the rational and elliptic curves. So where does that leave us?
I get the feeling from talking to you, as soon as a search space becomes finite, you become very despondent and lose hope.
Yes. It's finite because of this sort of general conjecture, but often finite can mean empty as well. And so it's entirely possible.
That's a type of finite.
That it's
the
not
worst.
just finite, it's just isn't
the worst type of finite.
A set of points. So somehow the moral of this story is that either we need to find some more of these rational or elliptic curves on the surface and hope for the best. There's only a finite supply of them.
I always hope for the best.
We can't just keep trying this all the time. And in fact, we might actually get a complete list at some point of all of these. And then, we really understand rational points on rational and elliptic curves. So once we have that final list, we'll be able to ascertain whether, you get one of these magic squares of squares, at least sort of from that point of view. Or the other hope is that, well, we do this and we find nothing, but somehow there's this miracle. And for some reason that we just don't understand, there's a couple, one or a few more sporadic points on the surface, all of whose coordinates are integers. But everything we know about the geometry of surfaces and the geometry of curves is really pointing to the idea that
never trust the sporadic points.
Magic square of squares.
Unreliable.
In the way that we would like it, with distinct integer coordinates, which is kind of sad. But I want to end on a good note, though. So.
Oh, thank goodness.
I need one more piece of paper.
Okay.
So what I want to show you is something that's kind of mind-boggling. So we've been asking for magic squares.
Okay, that was a very funny title.
3 by 3 grid.
I take back all the sass I said about Brady.
That the columns, the rows, and the two diagonals added up to the same thing, and all the entries were squares. Okay, but now we can go for broke here.
You got a 4 by 4 now.
You got a 4 by 4 now, and this is kind of amazing. Okay, so this is a 4 by 4 magic square of squares. This is not a fake magic square of squares. This is the real deal. Due to Euler, around 1770, thereabouts. These magic squares of squares have a very long history. If you look here, sort of all the rows, all the columns, and the two diagonals add up to the same number, 8515. So this is kind of crazy. There's a 4 by 4, but there isn't a
so
3 by
close.
3. Okay. And if you go on the internet, you'll also find a 5 by 5, and a genuine one, not a fake one, and if you dig far, there's also a 6 by 6, and so on. From the geometry point of view, this is actually not too surprising. In fact, I would actually think it'd be really cool to show that if you take an n by n grid, then, and n is at least 4, then you can produce one of these magic squares of squares. And so...
What happened when you kicked up? Because I thought if you applied that same process you just showed me,
right,
to this, you'd have the same problem. You'd come up with a surface that was really constrained.
So I picked the only
right. So let me just
dimension
explain briefly. Right. So if I have
where
an
it's
n grid,
can't be done.
I'm going to have something like.
To be fair, I deliberately picked a 3 by 3
and entries this way
because that
and
was
entries that way. Okay. So if you
the most
have an
open
n by n
question.
Grid, you have n rows, you have n columns, and you still only have 2 diagonals. Okay. But now, okay, how many variables do you have? Well, there's n times n, so there's n squared variables. So in the 3 by 3 case, there were 9 variables.
It goes up faster.
In the 4 by
That's
4
nice.
case, there were sort of 16 entries. So if you work on an n by n grid, there's going to be n squared variables. Okay, so what has happened here is that the space in which we're working in, right, the number of coordinates that we're going to need is growing really fast. But the number of conditions that we're trying to impose on that space is not growing anywhere near as fast as the space itself. So the space itself has dimension n squared minus 1. And then I have 2n plus 2 things that I need to set equal to each other.
So the Parker surface is no longer two-dimensional.
Exactly. It's no longer two-dimensional.
It's like a huge blob.
Exactly. It's like a huge blob, right? Right. We go up one dimension to n equals...
A lot of Parker things are often described
4,
that way.
Right? And now we're in 15 dimensions. We've made roughly 8 tuts. And so it's like a big blob. It's not a surface anymore.
Parker blob.
Yes.
The
that's
Parker
right,
blob.
The Parker blob in n dimensions. And so the cool thing, though, is
The n-dimensional Parker blob.
that we have about points on these
That was my
blobs,
nickname in high
it's
school.
not a surface anymore. It's a much bigger blob. And so things get harder and harder as these dimensions go up. But the main point is that the geometry of these spaces, as n grows, it actually becomes more positively curved, which means that it can harbor tons and tons of these kinds of rational and elliptic curves. And so
As I get older, I get more positively curved as well.
As n grows, we actually suspect there are lots and lots of points on those blobs. And so it's sort of not too surprising from the point of view of geometry that you would find a 4x4 magic square of squares, or a 5x5, or a 6x6. You know, in fact, it'd be really cool to prove that you can get an n by n for n at least 4.
Now,
Yeah.
do you know what would be cooler? Finding some number out there, n by n square, where there isn't a solution again.
Oh my God, that would be
What?
amazing.
Like
That
some,
would
by
be-
some
Nah.
freak curve.
Yes, that's right. And that could happen because, you know, in fact, these spaces are very singular. And so sort of the notions that we have about what ought to happen may or may not work in those spaces. I mean, we sort of think that probably it's going to be okay, but we don't really know. And no one has really sort of sat down to explore these spaces. There's some really interesting mathematics.
Get onto it.
At first, it might seem like, oh, we're just having some fun with squares, but there's some really deep geometry that's going on behind the scenes. And in fact, I can't resist saying this, but this square that Euler came up with is really important in the proof that every integer is a sum of, every natural number is a sum of 4 squares. There's a very famous theorem of Lagrange. In fact, Euler sent this particular square to Lagrange with no explanation about how he had constructed it.
Classic
And then,
Euler.
Lagrange had to kind of work hard, and then, Euler eventually did publish the method, and then once Lagrange saw what Euler was doing, he was really able to complete his proof. But it's amazing to me that sort of this that might seem just like pure fun actually ends up having some really sort of deep and interesting consequences.
If you find all the finite curves on there, rational and elliptic,
Yeah.
and they don't throw up what you need, can you prove...
And the
there are
finite other
those-
points.
Can you prove that there are none of those other points floating out there? Is that provable? Can you say, yeah, there aren't any points as well, or are they always going to be a bit of an unknown?
With current mathematical technology, I would not know how to do that. And I think that's sort of, just in general, it would be great to have some kind of mechanism to do
That's where I exist. Beyond the frontier of current mathematical knowledge.
can I find this sort of hypothetical set of finite points?
Parker points.
The Parker points, if you want, yes.
The Parker points.
Look, I know what you're thinking now. I want to see Matt Parker react to this reaction video. Well, don't worry, we've got you covered. We've put that on Matt's second channel, Matt Parker 2. You can find links in all the usual places. Go on, you know you want to.
So there you are. I hope you enjoyed me reacting to that video here at the Matt Reacts channel. Every video deserves an equal and opposite reaction video. And don't forget, I always see these things. Never watched them before. Watch it for the first time. You watch it with me. We have a lot of fun. Hopefully I don't get demonetized. And up next episode, we will be reacting to this video that you've just seen, which I've never seen. I've been in it, but I've not seen it from the outside. So stay tuned.